Mr. Crispin here once again, and welcome to my workshop. Now in today's video we're going to finish the cylinder blocks off for my locomotive, and this is going to involve a bit of drilling, a bit of milling and plenty of looking for the scriber. Now as a bit of a refresher, we're going to take a look at some footage from my old workshop, then I'll show you where we're up to and what's left to do, and then we'll complete them. So hope you enjoy watching. Okay, I'm now ready to Loctite the liners in. I've done a couple of little jobs, one on the cylinder block. I've drilled and tapped holes right on the divide between the liner and the block, and I'm going to insert a grub screw in there to act as a French key and just give a mechanical lock for the liner position. Also, I've degreased everything ready for Loctiting, and I came back a few hours later and this cast iron's gone bright orange. But the other job I've done is I've milled these pockets out, and hopefully you'll now be able to see how the steam goes. Comes into this liner, travels out of these radial ports into these cavities, and those cavities correspond with the steam ports, so that's the general flow of steam. I'm going to do the Loctiting off camera just because I want to do it slowly and carefully, and then I'll show you when I'm done. Well, slowly was definitely the word. Several years have passed since that bit of footage was taken, and here we all are again. Now here is a cylinder block with its bits in it, and the order of operations is as follows. First of all, I have to re-establish the exhaust ports. You know, these exhaust ports are now blocked up by the liner, so I've got to mill back through to establish exhaust route. We've got to bring the steam in. That's going to come in from the boiler at 60 degrees to the vertical, and it's going to go right in the middle of the block, so we need a tapped hole and a spot face in there to take a pipe fitting. We need a series of 8BA tapped holes around both edges to accept the cover plate fixing screws. There's a cover plate that fits over this at the end, and we've got to sort the bore out for the liner, finish bore and hone it in situ and get it square and positionally correct to everything else. Now in terms of the order, you could pretty much do this any way you wanted because all these features are independent, but something to think about here is the burrs. If I finish bore this and then do my milling and drilling, I'm going to be pushing burrs into the line of the finished bore, which we don't really want. So if I do my milling and drilling first and then finish bore it, it will be pushing the burrs away from the line of the bore. Still not perfectly ideal because it's going to leave me burrs that are going to be very hard to get to. So I'll discuss that a bit further when we get there. Now I was actually very tempted to mount this whole thing back on the mandrel. If you remember, to do all this radial milling, I had this on a mandrel to get all around it, and if I mounted it back on that mandrel, I could actually get to just about every feature I need to machine and do the whole thing in one setup. But I don't really want to start holding this finished bore again on a mandrel and say messing around with the dividing head. So I'm going to do this in a vise, and I'll just show some other methods for holding the component. So first up, the exhaust ports. You can see here we have to produce a slot that goes all the way through. Currently the slot only runs through the steel, the liner is intact. Now you can see on this other detail that they're two fairly narrow slots with fairly small corner radii. Probably isn't required, but I've gone for a 4mm radius so I can use an 8mm cutter. I'm going to start though by using a slot drill and just plunging out what material I can. Then using a long series end mill, I'll finish the profiles. Now these have been knocking around for a while, so I'm just going to regain some flat surfaces. I'm actually going to clamp these on the ends of the liner, as you will see shortly. And by clamping the ends of the liner, not only do I save messing around with all this other geometry, but I'm actually clamping the thing into which the machining forces are going. I've broken through now, and I'm now going to take them out to full size using a 5/16 end mill, but I have a problem with this cutter. And the problem with this cutter is, although it has the length, this portion here is actually a larger diameter than the cutting diameter. So I'm going to do a relief grind on this section so that when I come up to the side wall, this is in clearance and is not rubbing. Problem resolved, and back on with the job. Well, sorry if you're hoping to see more, but your view was as good as mine. I was fairly successful, not bad for a beginner, and you can see we now have the passage going all the way through. With the ports now done, we can turn to our steam inlet, and this requires a angular tapped hole. It's purely for a pipe fitting, so high precision of the angle isn't required. I've shown many a method in previous videos for accurately setting angles, but for the purposes of this pipe, a machinist's protractor will be perfectly adequate, sat on the fixed jaw and used to set the components. So I've set a bit of drag on the faces, and I'm now going to use my protractor to set the angle. These grinding vices are very good because as you tighten them, the forces go downwards, so there's no cockling of the jaw and no lifting of the component on the moving jaw side. So I'm happy with that, and examining it for any light coming through from the back, that's fine. Now that's well clamped, but to be on the safe side, I'm going to set a small adjustable parallel just so the component can't move downwards at all. So that's set in there, it's a snug fit, and should any excessive force press down on the component, it can't really go anywhere. With our component now set, I need to find our drilling position. I need to be on the centre line of this bore and on the centre line of the block, so right about here. Now you could obviously use an edge finder to do this. I'm going to show a different method using a DTI or clock, and I started explaining how to go about this, and I decided there were that many little details I would do a video in its own right, and I will release that shortly. It will be called Edge Finding with a DTI. For the purposes of this video, I will just very briefly show the method, and then we'll move on to drilling. And you can visualise this somewhat like finding a bore, and what I mean by that is we are going to touch on one side, sweep round to 180 degrees away from it, and whatever the error is, we're going to adjust it to get the clock to read the same on whatever side you're on. That will put the spindle on the centre line of that diameter at that point. And likewise the other axis is also being set by sweeping between the two faces with a clock in the spindle. To start the proceedings, I'm going to give myself a little surface with an end mill to start working from. If I had a proper spot face, I would use that because it gives you a truly flat surface. Using an end mill to plunge invariably leaves you a convex cone from the clearance angle on the end faces of the teeth. So there is a little spot face, and if you see what I mean, there is actually a little convex cone in there, which is one of the reasons why using a milling cutter to produce a counterbore is not always the best idea. And at this stage I'm just going to do a bit of a safety check to make sure I've not ended up being a whole turnout or something silly like that. That's okay. So we're going to proceed and drill this hole. taking it out to the tapping drill size. For tapping this 1/2x40, I'm using the Dave Ticehurst tapping chuck. So I have a piece of 3/8 silver steel in the spindle and a hole reamed in the end of this chuck, and I use that as a guide to keep this tapping chuck square as I'm tapping a hole. If extra force is required, a spanner fits nicely on this hex and can be used to drive. So that is that. We're all done here. Counterbore's done and on to the next operation. Now, I nearly forgot about the cylinder drain cocks, or at least the tapped holes for them. And the cylinder drain cocks are positioned here and here, and if you notice, we have a tapped hole and then a tiny little passage running to the extreme ends of the cylinders, both ends, and that is for when you start up cold. Steam comes in, condensates in the cold cylinder block and forms into water. You really need to get rid of that because too much water will obviously cause a problem with your piston. So you have a valve system whereby you can open these drain cocks and steam pressure will blow the water out. Now, I've come to look at the details of these and I've found a problem. The hole for the cylinder drain cocks has to go at 6 o'clock down here because that's where the water settles, but I've already put a tapped hole in, and if I try and put another tapped hole in here, I'm going to have a bit of a mess. The cause of this error is that I tried to space the holes such to miss this passage. Perhaps I should have rotated them around a bit more to leave this area clear, but not to worry, the willing man will find a way. And what I'm going to do is I'm going to move the cylinder drain cocks in this plane backwards 165 thou, and then between these problem holes and the tapped hole here I will have 50 thou, 1.25 millimeters. It does give me the added problem of having to drill a compound angle, because I've got to put an angle in it this way as well as that way. The blue passage is what I've got to drill, so we'll deal with that shortly. First up though, I'm going to put these tapped holes in 3/16 by 40. The operation is exactly as I've just shown, counterbore, tap. So I'm going to do that off camera and then we will proceed with these compound angle holes. So there's my tapped holes as per the diagram, and also as per the diagram I now need to drill a compound angle hole that runs from the centre line of this bore down, missing the hole and ending up intersecting the end of this hole. Now the proper or technical way to do this is fairly involved, and I know a lot of people don't like the maths, so I've taken all the video on how to do this and put it in another video called Drilling Compound Angles, which you'll be able to watch very soon should you choose to. But for the purposes of progressing with these blocks today, I'll say the following. So I have calculated a start point and an end point, and those 2 points describe the angle I've got to drill at. And to help me explain this, here's what I did earlier. And I'm going to put this little drill bit in there to show you that it's a rather horrible angle because it's not in line with anything. This is the datum I've used for just about everything so far, and it's pretty much square to most things and centre lines. This, however, is not square to anything, and that's pretty much what makes it a compound angle. Now, the name of the game here is to get the hole axis in line with the spindle axis. If you can get the hole axis and the spindle axis in line, then you can drill that hole at that angle. Now, there's lots of ways I could do this, and I'll demonstrate a few of them. I could set this on the bed and clamp it down, having rotated it to get one angle out, and then rotated the spindle round to get the other angle out, and I could then drill straight down that axis. Equally, I could mount this on a sine table or angle plate and tip it one way, tip it another way to get the hole truly vertical, and then just approach as normal. What I've opted to do in this case, however, is to mount the component vertically and then twist it in a vise. So that has now put our spindle and hole centre on top of each other. Now how you end up in the right place is the tricky bit, and that's what I'm going to show in the video coming up. And if you're really opposed to the maths, what you could do is scribe out the start point and then put a pointer in your spindle and line the two up, and then do a bit of hoping, and over such a short distance like that you should be fine. I will now move on and drill some holes. So hopefully you can see what happened there. You always get some interesting geometry when drilling into a curved surface on an angle, but we will have this extracted and have a look at it. So you can see there we've come in on the centre line, and we have broken through at that angle to produce our hole. See it in the back there? On to the final machining operation now, and that is to finish bore the piston valve liner. Now I'm doing this in a line boring setup as demonstrated and explained in part 2 of this series, and basically we have a bar supported between centres driven by the headstock, and in the middle of this bar we have a high-speed steel cutting tip, small nose radius, etc., and this is locked in place and adjusted by means of grub screws. So the further out you bring the tip, the bigger the bore it cuts. This bar rotates when powered by the spindle, and the workpiece feeds over it. A good method of boring, you get a highly parallel bore even on a small diameter to length ratio like this, and partly down to the tooling designer here as well, it allows me to get all the bores in line with each other and to interchange the components and get the bores positionally consistent. So I'm going to do a bit of boring and then I'll show you a little trick. Well, with a bit more boring done, here's the trick I wanted to show. Now, apart from being parallel, what really matters here is that the bores are the same size, and here's how I do it. I've bored this one to 3 thou undersize, and I'm now going to swap the components over. I'm then going to bore this one to say 3 thou undersize, at which point I'm going to re-stone the tool so it's nice and sharp. I'm then going to finish this bore and then swap the components back over and finish this one without disturbing the bar settings. So in other words, both bores are going to be finished with a sharp tool and an undisturbed bar. That should give me a good finish on both and the same size on both, and I'll demonstrate that now. Now with M12 studs here I could do a bit of damage to the component, or in fact the cross slide, so light pressure on them, and then I'm going to check my positions against the gauge and faces with a 1 thou feeler gauge. All okay, so I'm now going to reinstall the bar and bore this out to almost finished size. Down to the last cut now, and I'm just going to resharpen my tool, set the finish cut to diameter, take it, then swap the blocks over. Delicate adjustment of the cutting radius can be done using a clock set with the stylus in the truly radial direction. Finish cut number 1. This will be spring cut number 1. Well, my surface finish detector says that's acceptable. Finish cut number 2 and spring cut number 2. To finish the job, I'm turning my attention to the two little bores that lie on the ends of this liner. Now fittings go into those bores, so it's very important that everything is concentric, as you'll see later in future videos when we start assembling things. So what I've opted to do is to take the tool and regrind it almost to an Acme profile, and I'm just going to skim the bores very lightly, take a little finishing cut just to get everything in line. That's it, I have reached the end, and if you've managed to watch all 8 parts of this series in their entirety, then well done. You are welcome to send off for your medal. Now I did mention briefly that I was going to talk about deburring. As it happens, I haven't needed to, but I'll show you very quickly what I was going to say. Now if you look down the bore, you can see there's all kinds of entrances and exits and ports and passages. Now were this a more malleable material like mild steel, as I bored this it would have folded burrs into those passages, and they'd be rather tricky to get out. So what I was going to do was deburr the insides of this with a file or something similar before I took the finish cut, and I would deburr them extra deep so that when I took the finish cut it brought them down to a proper size of deburr. But being cast iron, it's been rather brittle and hasn't really left me any trouble. Well, there's the finished articles. I'm rather pleased with them. A lot of time and thought's gone into these, and I'm happy with how they've come out. I'll probably do a conclusion video later in the future, just with a few points I didn't get a chance to mention. But until then, I hope you've enjoyed this cylinder block series, and see you on the next video.